Okay, so today we're going to be looking at mathematics in nature, and I want to focus on an example of a sunflower. And I want to know, how does a sunflower know what angle it needs to spread its seeds at? So here we've got an example to start off with. So if it spreads each seed at a half turn, then you're going to get one seed here, another seed there, but by the time that you've turned again, you're going to be back where you started, and then this is going to repeat. So okay, that was a half turn. What's going to happen if it's a different angle? Well, if it does a fifth of a turn, then we're still going to get these spokes that we see. Okay, and then again, if you do a third of a turn, you're going to get them again. But obviously this doesn't look like a sunflower petal. So how does it know which angle to grow at, and what is that angle? Well, we use this very important number in mathematics, called the golden ratio, written as this Greek letter phi, and that's how we find it out.
And it was first discovered by the ancient Greeks and documented in the 3rd century BC by Euclid, who was responsible for a lot of the geometry work that you do nowadays. And it's said to represent proportional beauty. Okay, so for those of you in Key Stage 4, you might have studied proportions. So when it comes to proportional beauty, this is the ratio that you would see such a thing in. Okay, and that just means it's very aesthetic to look at. And it's also the solution to this quadratic equation, x squared minus x minus 1 equals 0. But how does it actually relate to nature? Well, before studying that, we can look at the Fibonacci sequence. Now, you might be well aware of this sequence because it is famous, and it's given by the sequence of numbers is given by adding the two numbers before a number in the sequence. So if you wanted the 5th, for example, you'd add the 4th and the 3rd together. And it looks like that. So 1, 1, 2, 3, 5, 8, and so on. And this is an infinite sequence, so it never ends. Well, you might ask, well, what's that got to do with anything? Well, if I take two numbers that are next to each other in the sequence and divide the bigger by the smaller, you can see in the picture that they slowly start to look more and more like the golden ratio. So what we say is that this new sequence that we've got actually tends to the golden ratio. So eventually it will look so much like it that you won't be able to tell them apart from just looking at them. So now we've got this really strong link between the golden ratio and the Fibonacci numbers. And we can see it in nature. So if you look at the pine cone in the top right of your screen, and we're looking at the spirals of it. So in the clockwise direction, there's 13. And in the anti-clockwise direction, there's 8. Well, what do we know about those numbers? Well, they're both Fibonacci numbers. So if you divided through by them, it'd look similar, or be a similar number to the golden ratio. And that's the same that you can see with the sunflower head there, with the spirals of the seeds. So 34 and 21 would close approximate the golden ratio.
So now we've seen where the golden ratio relates to Fibonacci numbers, but this could just be a coincidence. So let's look at more examples. So we can make this really nice rectangle called the golden rectangle, which has proportions with the golden ratio. Now if we took this square out, what we find is we get this other rectangle, which has still got the proportion of the golden ratio. We can do it again and again and again until we get towards this centre. And then we can make this really nice spiral called a logarithmic spiral. Well, this spiral is something that occurs very often in nature. So for example, we can see it in galaxies. So the spiral arms of the galaxies look like the spiral created by the golden ratio, the logarithmic spiral. We can also see it in other examples in nature, like a Nautilus shell. So essentially what this is a little octopus that grows inside a shell. Obviously as the octopus grows, it's going to get larger and larger, and each chamber is to do with how large it is. So it grows proportional to the size, which means we get this really nice looking spiral. Okay, so now we want to look at why does this happen. Well, to look at why this happens, I'm going to first look at the number pi. So you'll know this from looking at the area and circumference of circles. So when I look at pi is this irrational number, which is 3.14, so on and so on. So I can split that up, so it'll be 3 plus this decimal. We can think, how can I write this? Well, I can then write that as a fraction. And what we're going to do is we want 1 on top of this fraction. And we find that then again, on the bottom, we're going to get some never-ending number. So we split it again. We think, what can we do? Well, we'll do the same process. And we start to get a fraction on a fraction on a fraction. And this might look very messy. So what we'll do is just skip forward a bit. And we'll see that at some point, we get this really big number. Well, what does that mean? Well, it means that if we were to stop this at some point, and say we'll stop it there, if we stop it there, then because this is such a small number, because the bottom of this fraction is so big, it doesn't have much significance in terms of the overall thing. So this number will still look a lot like pi. So what's going to happen when we do it with our number that we've got the golden ratio? Well, if we split this up, it's going to be 1 plus all this, so 0.61. You might think, okay, how are we going to write this as a fraction? Well, a nice thing about the golden ratio is that when we write it as a fraction, we're just going to get the same thing again. So we're just going to get the golden ratio on the bottom. So it's again going to be this. And you'll start to notice a pattern when I'm doing this. 1 plus 1 over 1 plus. And what we're going to find is that because this is an irrational number, this will never end. But also, we've constantly got these ones. So unlike when we looked at this, and we saw that this part's never going to be significant, here, because it's such a small number, it's always going to be significant. Which means that if we stop it at any point along this, no matter what point we stop it at, it's going to be very hard to make it actually look like the golden ratio. And because of that, that is why plants and nature uses this so often, because it is so hard to approximate the golden ratio. It is so hard to make it look like a fraction. So now that we've seen how we can explain the golden ratio's appearance in nature using irrational numbers and the continued fraction version of the golden ratio, we can look back at that sunflower seed example. So using this online product that someone has made, well, someone from Numberphile has made, we can show what would happen at different angles. So if we took the angle where we take a fraction of 360 degrees of 0.1, like I showed you before, then again you can see that you get those 10 spokes or 10 prongs. So now what we want to know is why the golden ratio. Why would the golden ratio work best? So if we start this running from 0.6, then what we'll see is that when we approach 0.618, which is equal to the golden ratio minus 1, then it would actually look the most like the spread of the sunflower seeds. Why are we picking 0.618? Well, this is because if we picked 1.618, then when we go around an entire once, it would just land us back at the place we were at. So we take away that 1 and go with 0.618 to get that extra turn. And we can see there that the actual angle that is necessary, is the golden angle, is 137.5 degrees. And there you see it gives us an almost perfect match for the spread of the sunflower seeds. So now we've seen the golden ratio in nature, and specifically why we see it so often in nature. That being, the golden ratio is so hard to approximate as a fraction, which is the main reason why it applied to that sunflower example that I showed you. Now, some people say that this is completely false. We don't see it in nature because we just see approximations. But I think more people would argue that from observations, it is true that it is in nature. I hope you've enjoyed this, and thank you for listening.